Dr. Musthafa, Dr. Tanya Francis, Dr. Manoj Matthews, all the dear teachers and dear students. So we'll be having the last session of electrochemistry, last class of electrochemistry by Professor Musthafa from IISER Pune today. We'll be concluding this session here. And dear students, please make use of this. You will not get such an expert in near future, I think, for such a free interaction. So please make use of that. Our next class in this series will be in the third week of October. There will be no class in the next week since we have Puja holidays. We'll be having the next class in the third week of October, and that will be moving from physical chemistry to organic chemistry. The resource person is Professor I.T. Biju from Indian Institute of Sciences. He will be teaching oxidation and reagents for oxidation and reduction reactions in organic chemistry. So this is after a few physical chemistry classes, we will be moving next to organic chemistry. So in today's class, at the end of this session, we will share a feedback form in the chat box, and as well as the feedback form will be there in the description part of Google YouTube videos, which we are sharing. We are live telecasting that, and also that is shared to the participants. So we should fill the feedback form just to inform us how it is going. Okay, with this, welcome again, Dr. Musthafa, and over to you.
Okay, thank you, Dr. Jomon. So I shall share my screen now. So if you are able to see it, please do let me know. Okay. Can you see my screen,
Yes,
Jomon? Yes. Okay, thank you. Okay, as Dr. Jomon rightly said, the happy news is this is the last electrochemistry lecture. Okay, so I don't want to kill your happiness. Okay, so let me directly jump into the topic. Electrochemistry fundamentals, and yesterday we were talking about the development of electrode potentials and the consequences of that electrode potentials in electrochemistry. And electrode potentials offer a plethora of opportunities. You can actually measure the thermodynamic parameters using the principles of electrode potential. You can predict the spontaneity of a chemical reaction using the electrode potential measurement. And I discussed how do we construct the electrochemical series, and also how do you construct a battery by taking a negative electrode and a positive electrode from the electrochemical series. And the construction of batteries is like the construction of a two-bedroom flat. It is very simple. All right, and today, let me move on to the next aspect of electrochemistry. Even though electrode potential offers a lot of opportunities, there is one area where electrochemistry finds immense application, that is in the domain of pH measurement. And I would like to briefly discuss about pH measurement. Whatever the pH measuring device that you see around are electrochemical in nature. Most of them are electrochemical in nature. And I would like to briefly mention how do you measure or what is the principle behind the electrochemical pH measurement. To demonstrate that, I use what is called a quinone-hydroquinone redox couple. Okay?
Dr. Musthafa?
Yes. Jomon, I can't hear you.
Actually, Jomon sir is mute. Only now the slides are visible.
Okay. What was the problem, Jomon?
There was one question yesterday.
Yes. Okay. Let me. Can I come to that in the last part, Jomon?
No problem.
All right. Okay. I remember that. Okay. Yes. So now let me outline the principle behind pH measurement. Just by taking the example of quinone-hydroquinone redox couple. So this is quinone molecule. One second. There is some issue with my presentation. Okay. Sorry for that. Okay, this is my quinone molecule. I'm going to write here on the screen. Okay. And if you reduce this molecule, you will end up with hydroquinone. Okay. So this I name it as Q. This I name it as QH2. And you can see when you move from left hand side to the right hand side, there are 2 protons extra in front, 2 hydrogen extra. One here, one here. Which means on the left hand side, you have to add 2 protons and 2 electrons very simply. And your electrochemical equilibrium is ready. For the quinone hydroquinone redox reaction, your electrochemical equilibrium is ready now. And if you write the next equation for this particular, so let me rewrite this equation as Q plus 2H plus 2 electrons going to QH2. This is the electrochemical equilibrium for the quinone hydroquinone redox couple. And if I write the next equation for this redox couple now, it will look like E is equal to E0 plus 2 point. It's a very simple one. You know that 3 RT by 2F, because number of electrons are 2, you can see here, into log of concentration of quinone, concentration of H plus, the whole square divided by concentration of QH2. Concentration of H plus the whole square because you have 2 protons involved. That is why. Okay. Now, if you use what is called quinhydron, there is a complex called quinhydron, which is actually an equimolar mixture of quinone and hydroquinone. If you use quinhydron for doing this measurement, which contains equal concentrations of quinone and hydroquinone, this equation will become now simply E is equal to E0 plus 2.303 RT by 2F into log of concentration of H plus the whole square. Because in this case, the concentration of quinone is equal to concentration of QH2 and both will cancel out like this. So you are left only with H plus now. Now, if you rearrange this equation, because it is concentration of H plus the whole square, you bring the 2 to this side, and this equation will become E0 plus 2.303 RT by F into log of concentration of H plus. And you know, negative log of concentration of H plus is pH. And if you put this equation into this equation, it will become E0 minus 2.303 RT by F pH. E is equal to. This is a very, very important relation. Most of the time, it used to come for many competitive examinations. You can see on the left hand side you have the electrode potential, or on the right hand side you have the pH. And this equation simply says that if you plot the electrode potential, if you make a graph between electrode potential and pH, E and pH, if you make a graph, it will exhibit a negative slope like this, because it is minus 2.303 RT by F pH. So what you do is that you take non-pH solutions. You take non-pH solutions, okay, and simply measure the electrode potential and construct the calibration plot. You take non-pH solutions, okay, simply measure the electrode potential, construct this graph, and take your unknown pH solution, simply measure the electrode potential. And suppose if it falls here, just extrapolate it. You will get the pH of the unknown solution. So this is simply the principle behind the pH measurement electrochemically. And whatever the pH meter you see around, most of the time, it is measured electrochemically, but the difference is the electrode is based upon the glass electrode. I just want to emphasize that point before going to the last part of the topic today. The last part of the topic is an exciting part that is called electrochemical double layer theories. It's a very, very important aspect of electrochemistry. I would say it is the heart of electrochemistry. And you know that electrochemistry begins as soon as you dip an electrode into the solution containing ions. And the one phase contains electrons, the electrode phase contains a lot of electrons, and the solution phase contains a lot of ions. And there is a possibility that electrons can cross the interface from the electrode to the solution phase. If that happens, the electrode will acquire a positive charge and the solution will acquire a negative charge. Solution will acquire a negative charge means what? There will be more anions near the electrode. That is the meaning of negative charge means. Please do not forget that. So you can see there is a layer of charge on the metal side, plus charge, and there is another layer of charge on the solution side. Therefore, this interfacial region is often called as electrical double layer region. And the formation of electrical double layer is actually the fundamental act in electrochemistry. Do not forget that. The formation of electrical double layer is the fundamental act in electrochemistry. And the electrochemical behavior of any electrochemical interface is very, very sensitive to the structure of this electrochemical double layer. If there is a minute variation in the structure of the electrical double layer, the electrochemical property, the electrochemical behavior will be dramatically altered. And if you want to manipulate, for example, your battery, if you want to manipulate your battery to make it more powerful, you must have an idea about the structure of the electrical double layer of that electrode. Otherwise, you cannot manipulate it. You cannot make it powerful. Whatever you want to do with your electrochemical interface, let it be battery, supercapacitor, fuel cell, or whatever be the electrochemical device, if you want to manipulate it, you must have an idea about the structure of the electrical double layer. It's very, very important, because that dictates the property of that interface. And experimentally, I would say it is very, very difficult to estimate the structure of the electrical double layer. For that reason, there are many theories available to predict the structure of the electrical double layer, and those theories are called electrical double layer theories. Very complex theories, very difficult to understand. I know now many people will leave when I say very complex, but I will tell you, you will understand, all these theories in one look if you understand the relation between Ambani and Becker. I hope you know Ambani. Ambani is a super rich guy, billionaire, billionaire. I don't know what is the amount of crores he has. He's a billionaire, Ambani. Becker is a beggar. He doesn't have anything. If you know the relationship between Ambani and a beggar, you can understand all these theories. Why? Because metal, we are talking about metal, is a super rich guy. There is a reason why he's a super rich guy. Super rich guy. Why? Because according to electron C model, metal is described as metal ions swimming in a sea of electrons. Metal ions swimming in a sea of electrons, which means metal is a super rich guy with electrons. It's a very important point. So like Ambani, okay, metal is also a super rich guy, but with electrons. What about solution? Solution contains a few ions, some few ions. He is not a super rich guy like metal. So solution is like a beggar. Please keep that in mind. This is very, very important. Otherwise, metal is like Ambani, solution is like a beggar. Keep that in mind. Why? Because metal is super rich guy with electrons, solution is like a beggar. Now, okay, if anybody wants to see Ambani, I have a picture of Ambani also. Let me ask you a question. If Ambani donates 1 crore to a beggar one fine day, Ambani donates 1 crore to a beggar. The question is, what will happen to Ambani? I'm sure everybody knows. Nothing will happen to him because he's a super rich guy. Yes, he's a billionaire. Even if he donates 1 crore to a beggar, nothing is going to happen to him. If nothing is going to happen to him, my question is, should we worry about him? We should not worry about him. So the question is, we should not worry about Ambani because nothing will happen to Ambani even if he donates 1 crore to a beggar. So we should not worry about Ambani. What about the beggar? His life was very pathetic and miserable before getting the 1 crore. He was struggling to make the ends meet in his life. He was struggling for food. Nobody was looking at him. No girlfriends, no boyfriends, nothing was there. Simply a boring life. And one fine day, Ambani walked into him and offered him 1 crore. Can you imagine what will happen to his life after that? I'm sure his life would be transformed quite dramatically, quite miraculously. Maybe something like this. So something quite dramatic happens to the beggar. So I'm sure if something quite dramatic happens to the beggar, we should worry about the beggar for sure. Exactly similar situation will happen when you dip a metal into a solution. Mainly because metal is a super rich guy with electrons. Solution is like a beggar. So something quite dramatic happens to the solution side of the interface. Not much to the metal side of the interface. That is why all these theories are primarily concerned about the solution part of the electrical double layer. Because solution is simply the beggar, something quite dramatic happens to him, not to the metal. With this background, let me go to the first theory that is called the parallel plate condenser model or the Helmholtz-Perrins theory. Simple theory, I'll tell you. According to this theory, okay, I don't want to go to the mathematics and all because you will leave the meeting. I don't want you to leave the meeting. According to this model, you have a metal. Okay. And the metal, for example, if there is a positive charge on the metal side, according to this model, there will be another. So this is the metal surface. So suppose the charge on the metal is positive. What will happen is that according to this model, there will be another layer of charge on the solution side, which is equal in magnitude but opposite in sign. So the charge on the metal will be balanced by another layer of charge on the solution side, which is equal in magnitude but opposite in sign. But opposite in sign. And most importantly, the most important assumption of this model is the layer of charge on the solution side, this charge, is fixed and immobile. Is fixed and immobile. It cannot exhibit any movement. The layer of charge on the solution side means we are talking about the anions now, negative ions. According to this model, that layer of charge is fixed and immobile. It cannot move. Physically, it cannot move. So it looks like we are talking about, okay, this is one plate of a capacitor. This is another plate of a capacitor. So this model looks like a parallel plate capacitor. That is why this theory is often called as parallel plate capacitor model. It was a very elegant idea, brilliant idea, no doubt about that, because it was one of the first theories on electrical double layers. But the theory failed miserably to explain the experimental facts. There was no correlation between the theory and experiments with respect to this model, which means if it fails, so if the theory fails to explain the experimental fact, it says that the theory is not accurate, it requires modification. The interfacial structure is not like this, that is why it requires modification. What could be the reason why the theory failed? That is why people have looked at in the later part. It's very obvious. We are talking about ions in the solution. Ions in the solution are free to move. They cannot be fixed and immobile. As in the case of this model, they cannot be fixed and immobile as in this model because they are free to move in the solution. And that was the major mistake in the electrical double layer theory proposed by Helmholtz and Perrin. In the later part, Gouy-Chapmans tried to correct this model and they brought forward Gouy-Chapman's diffused layer model. And what they did was they allowed complete freedom for the ions to move in the solution. They allowed complete freedom for the ions to move in the solution. So according to Gouy-Chapman's model, you have a metallic electrode. Okay. Since ions are free to move, you will have more number of negative ions near the electrode surface because of the positive charge from the electrode surface. But as you move further, what will happen is that the electrode forces the charge on the electrodes. As you move in this direction, further away from the electrode, the field of the electrode will diminish and you will have less number of negative ions like this. So you can see it is not in a single layer now. The ions on the solution side is arranged in a diffused layer. You can see that because ions are free to move. And more number of ions are there near the electrode surface because of the charge exerted by the electrode surface. So you can see here in the Gouy-Chapman's model, the charge on the metal is balanced by a diffused layer of charge on the solution side. It was again a brilliant theory, no doubt about that. And this theory worked quite well only at low concentration. Only at low concentration. And the theory failed miserably at high concentration. At very high concentration, the theory failed miserably. Can anyone say why? From the audience, you can type in the chat box. Because when I ask questions, I see that many people are leaving. So it looks like I should not ask questions. All right, the theory works quite well only at low concentration because only at low concentration, you can have this kind of diffused layer formation. At very high concentration, what will happen? There won't be any space for this kind of diffused layer formation. So they will form a compact layer. So that is why the theory works quite well only at low concentration, not at very high concentrations. So the theory was successful to explain the electrochemical behavior only at low concentration, not at high concentration. Which means at high concentration, again, the theory requires modification. That is why the third model came into picture. The third model is an interesting model called the Stern's model. According to Stern's model, Stern was a fan of A.R. Rahman, so Stern's model is like A.R. Rahman's musical concept. According to Stern's model, the electrode-electrolyte interface looks like A.R. Rahman's musical concept. When you dip an electrode into a solution containing ions, according to Stern's model, electrode is like A. Rahman singing on the stage. And I'm sure your question will be, which song he is singing? Not about the interface. I have an answer for that because I'm smart. This song only. Now, when you dip an electrode into the solution containing ions, the electrode is like A. Rahman singing on the stage. What about the electrolyte? Electrolyte. So the electrolyte is like the audience responding to his song. If you go to any musical concert, you will see in the front row people like this, big people, you know, celebrities, businessmen, politicians, industrialists. All big people will be in the front row, and they will be enjoying the music without much physical movement. They will be enjoying the music, no doubt, because they pay money now. They will be enjoying the music, but without much physical movement. Very important. If you go to the back of the stage, you will see another group of people like youngsters. They will be enjoying the music with a lot of physical movement. Exactly same situation happens when you dip an electrode into a solution containing ions according to Stern's model. The layer of electrolyte, which is near to the electrode surface, will be fixed and immobile because of the force or field from the electrode surface. Because it is near to the electrode surface, because of the electric field from the electrode surface, the layer of electrolyte near to the electrode surface will be fixed and immobile. They cannot physically move. And as you move further away from the electrode surface, what will happen? The electrode field will diminish and thermal forces will dominate. Thermal forces are disordering in nature. So you will have a diffused layer of charge as you move further away from the electrode surface. So you have one layer which is fixed and immobile, and you have another layer which is diffused. So you will see immediately that Stern's model is a combination of Helmholtz-Perrin's model, the first model, and the second model. And this theory could explain most of the experimental facts. I mean, most of the experimental observation, this theory could successfully explain. And many theories came later part in the later part, which talks about the orientation of water molecules on the electrode surface, adsorption of anions, blah blah blah, so many things. I'm not going to those details. I just wanted to tell you that the structure of the electrode-electrolyte interface is extremely important in electrochemistry. Whatever be the electrochemical application you are talking about, it is very, very sensitive to the structure of this interfacial region. Therefore, one must have an understanding, a clear understanding about the interfacial region, structure of the interfacial region, without which he cannot make any major contribution to the electrochemical system he's working with. So you should pay attention to the structure of the electrode-electrolyte interface if in the future, if you are taking up electrochemistry as a career option. Now, you might be wondering, why this guy is talking about electrochemistry, electrode-electrolyte interface today, and in the past few days, he has been talking about electrochemistry. You might be wondering, why electrochemistry now? Why electrochemistry assumes great significance in the present-day world? Electrochemistry assumes great significance in the context of the historic Paris Agreement on climate change, where the world leaders have unanimously agreed to limit the global warming temperature to 1.5 degrees C. Why they have decided to limit the global warming temperature to 1.5 degrees C? This is mainly because of the adverse effects of global warming. Because of man-made activities, because of human activities, you can see these poor species have irreversibly lost their habitats. They are clinging on to the last pieces of their habitats now because of our own activities. And usually polar bears are ferocious and aggressive, and they are heavily dependent upon the ice layers to find their daily meal, to find their daily food. They are heavily dependent upon the ice layers. because the prey of the polar bear, seal, that seal used to hide under the ice layers. And when there is no ice, the seal won't be there, and the polar bear won't get any food, and it will starve to death. And because of global warming, you can see polar ice cubes melted away at a faster pace, and you can see this polar bear is going to die. It is starving to death, and it happened mainly because of our own activities, human activities, very deliberate human activities, I would say. Carbon dioxide is the major player in global warming. Increased emission of carbon dioxide by human activities have increased the accumulation of carbon dioxide in the oceans. Carbon dioxide dissolves in water as carbonic acid, which will decrease the pH in that locality. And because of this increased accumulation of carbon dioxide and because of the decrease in the pH levels, there are reports that the shells of shellfish and coral reefs were dissolved because of the decreased pH levels in that locality. Then comes the painful story of Midway Island. Midway Island is a very beautiful island somewhere in the remote Pacific Ocean. It's a very beautiful island. But the problem is it is located within what is called North Pacific Gyre. It is within the North Pacific Gyre. This is the North Pacific Gyre. This area is the North Pacific Gyre. And the Midway Island is within that. You can see here. What is North Pacific Gyre? Whatever the plastic, whatever the pollutants you throw out will eventually reach the ocean. From the ocean, it will be carried to what is called the North Pacific Gyre. It's a well-known fact. And what happens is that in the North Pacific Gyre, all the pollutants, trash, and the garbage will continuously swirl in global ocean currents. In the North Pacific Gyre, all the pollutants, plastic, and garbage, and the trash will be continuously swirling in global ocean currents. It will be swirling like this. And you see the location of the Midway Island. Midway Island is within the North Pacific Gyre. So what will happen? All the garbage swirl, and eventually it will accumulate on the beaches of Midway Island. And the Midway Island acts like fingers of a comb, according to a journalist, collecting tons of garbage on its beaches. So what is the problem? The problem is Midway Island is a home for a beautiful bird by name Laysan albatross. It's a beautiful bird with 6-foot wingspan. And for all the wrong reasons, these pollutants, trash, and garbage look very attractive for this Laysan albatross. All the garbage looks like food for this species. So they consume it. Once they consume it, they cannot digest it, so they will die. And millions of birds were killed by consuming plastic pieces. And recently, a group of scientists from Canada visited the spot. And when they opened the rib cages of a dead Laysan, albatross, they could find only plastic pieces inside. You can see when they opened the rib cages, they could find only plastic pieces inside the stomach. So these birds were punished, not for their mistake, but for our own greed for money. You might have seen this picture. This poor turtle, when it was hatched out of its egg, it got trapped in a plastic ring, and it had to grow up in the ocean with that plastic ring around its body. And you can see the middle portion got deformed. This again shows our casual indifference to the future of other species thriving on this ecosystem. Usually, turtles lay their eggs on sandy beaches. You know that. And the temperature of the sand will decide the sex of the baby turtle. Whether it should be male or female, it will be decided by the temperature of the sand. If the sand temperature is high, it will be female. If the sand temperature is low, it will be male, like that. And because of global warming, what happened is that the sand temperature has increased quite dramatically. And a recent survey shows that among the 117 baby turtles investigated, around 116 were females and only one was male. It's a quite alarming sex ratio. You must look at it. And this will lead to the eradication of this species from this planet. And we are playing with fire. Do not forget that. And this was covered in many magazines, across the world. This particular aspect of sex ratio was covered in many magazines and articles. And you might think that, okay, it's all about turtles. Why should I worry about it? The recent scientific analysis of salmon fish shows that there are microplastic particles in the flesh of salmon fish. It's a very popular fish in the European continent because it has got an orange texture. And people have found microplastic particles within the body of the salmon fish. And if you consume this fish, it will eventually, these microplastic particles will find a way to your body, and there it will accumulate, and it will lead to serious health complications in the future. So the danger is knocking on your doorstep. You must be aware of that. Remember one thing, that plastic is the end product of the same petroleum industry which is responsible for the global warming. Quite alarmingly, Canada has started exporting fresh air to China at a rate of Rs 10 per bottle. Fresh air to China. You will think, okay, China is our enemy, so why we should worry about it? This China, India, Pakistan, and all, exist only in the mind of the people. The land doesn't have any boundary. The land doesn't know that it is China, India, no. It is only in the mind of the people. Do not forget that. LG India and Honeywell India have already started manufacturing air purifiers for India as well. It is in this context electrochemistry assumes great significance for today's world. Because it is in this context people have decided to limit the global warming temperature to 1.5 degrees C. It is because of these reasons world leaders have decided to limit the global warming temperature to 1.5 degrees C. But to achieve this target of 1.5 degrees C, you must have to develop zero emission technologies. Zero emission means zero polluting energy technologies at least by 2050. To achieve this target of 1.5 degrees C, you must have to develop zero polluting energy technologies at least by 2050. And that energy technology should not be based on fossil fuel based energy technology, because fossil fuel based energy technology is responsible for the global warming. So we need to have alternative zero polluting energy technologies at least by 2050 to achieve this target. And fuel cells, batteries, supercapacitors, and solar cells are potential zero polluting energy technologies. That is why people are worrying about, that is why people are looking for electric vehicles all over the world, because they are zero polluting energy technologies. And all these devices, fuel cells, batteries, supercapacitors, solar cells, are electrochemical devices. Are electrochemical devices, and that is why electrochemistry assumes great significance for the survival of our planet. And I end my lecture here. And as I said earlier, we are a group of people from IISER Pune, and IISER Pune offers various platforms for young students like you, for various programs like integrated BSMS dual degree programs in science after +2, and master's degree programs will be started. So we'll be starting the master's degree programs in science after BSc in the next year, and we already have integrated PhD programs after BSc, and the selection is based on a competitive examination, and we have already PhD programs after master's degree, and I'm sure all of you are very brilliant students, because the kind of questions you asked, you have asked me only 2 questions, okay, but all the 2 questions were very brilliant. So the kind of questions you posed at me says that you have the potential to be in world-class research institution, and I strongly encourage you to appear for all these competitive examination and try to get into this kind of institutions for your future studies. Now, before winding up, let me answer one of the questions asked by one of the participant. The question was about the selection of the electrolyte in electrochemical devices. And it's I must tell you, it's a very brilliant question, because as Dr. Manoj pointed out yesterday, electrochemists often worry only about anode and cathode. They do not pay much attention to electrolyte. So, but the question of the participant is about the electrolyte. So I'm very happy that he or she, has thought about that subtle aspect of electrochemistry. Of course, electrolyte is extremely important for any electrochemical device. Mainly because, the stability of the electrode with electrolyte is extremely important. If the electrode-electrolyte combination is unstable, you may have to tune the property of the electrolyte. There is a major area of research in the area of lithium-ion battery, where the compatibility of lithium metal with electrolyte is still questionable. That is why people are exploring to develop new electrolytes for lithium-ion batteries. And when you come to aqueous electrolytes, the major problem is the potential window. The potential window means the stability of the aqueous electrolytes is very limited, only 1.23 volt. Beyond 1.23 volt, water will decompose. So you have only a narrow window, and people are trying to expand this window by various methodologies and techniques. And coming back to the question specifically, the question is, can we use any other zinc-containing electrolyte for Daniel cell application? Of course, you can, for sure. But you will have to think about the salt hydrolysis phenomena when you select a salt. For example, if you select zinc chloride, you should look at the salt hydrolysis. Zinc hydroxide, HCl formation will be there, all those things. And what is the nature of the salt? Acidic, alkaline, neutral, that should be, so you should look at it. And you should always select a neutral salt to deal with Daniel cell applications. And electrolyte plays a major role. You cannot, for example, you cannot dip a zinc in copper sulfate solution. You can dip zinc in zinc sulfate solution, no doubt. Not in copper sulfate solution. The moment you dip zinc in copper sulfate solution, there will be internal galvanic reaction. Copper will go, copper ions will go and displace zinc 2 plus ions from the lattice. So there will be copper deposition on the zinc plate. So the electrolyte is extremely important. Choice of electrolyte electrode combination is extremely important for electrochemical application. And I'm glad that you have asked this wonderful question. And you should apply for PhD programs and if you happen to be a student, PhD program in IISER Pune, and you have a future to be a great electrochemist for sure. Thank you very much for giving this opportunity to me. And I hope some of you have benefited from this lectures on electrochemistry, and you can get back to me for any questions if you have. Thank you very much.
Thank you, Dr. Musthafa, for a wonderful session. And from the students, if you have questions, please free to ask. When I have a general question.
Yes.
When some student comes for an interview there for MSc or PhD, what kind of question will you in the area of electrochemistry? I mean, to what level you will be asking?
See, if they have listened to my lecture, they will be easily selected. That is the answer. Everything is there. So it will be basically from all these things, and I don't think I will go beyond all these things because that is much advanced. Because see, there is something called electrochemistry of semiconductors. It's a very exciting area, but it is not at the bachelor's degree level. It is much advanced. But if they pay attention to this and they work on it, this is just a background information, not much. If they pay attention to it, I think they have a potential to be great electrochemist. And at least I want to see one electrochemist coming out of just participants. My life will be, if that happens, my life will be done. I'll get moksha, you know. Moksha is important in anybody's life.
Yes, yes.
It looks like nobody has any question today also.
The conceptualization of the electrode and the solution being Ambani and Beggar is I would say very very a new concept. So we've never looked at it like that. We've only thought about the electrode being connected to the positive being positive and the solution having a opposite charge. So the conceptualization is excellently done, and I think the students should keep asking questions, which they don't do.
Thank you, Dr. Tania, for your wonderful statement about the double layer theory, because it is the heart of electrochemistry, means it is my own heart now.
Yes, so true. So true.
So,
Jovan sir, I don't think there is any more questions coming from the student side.
Yeah, and at least from someone from teacher's side. Yes.
but I expect a statement from Dr. Manoj.
Yeah, I mean, it's on the way.
Yes. I reserved my comments because I am also officially given a responsibility to propose the vote of thanks.
Okay, good.
Yeah. Okay, students, so let's wind up the session. So I think this was an excellent session, both from the aspects of electrochemistry fundamentals and also as a teacher. We can see always, rather than delivering just the concepts, when if at all you can relate to such, right from your the Kareena Kapoor to the latest Ambani version, actually students can easily get connected. So it is really the talent of the teacher. That is the reason why IISERs are actually getting a teaching plus research integration, so that all the teachers coming from IISERs have that particular knack of teaching well, and that we are experiencing that. So we are very extremely happy that you had accepted our invitation and you have delivered us a very energetic, enthusiastic talk on this. And as you said, even our purpose will be served if some of the students will be taking up this opportunity. And SICRI is the very famous institute. We always advocate students to go there and do research on this topic. But we also now have another very important person whom we can very safely send our students to for research. So that is the achievement what we had. And also, I think Dr. Musthafa will accept our invitation where he has talked, because we are also very much interested to have a specialized talk on capacitors, fuel cells, and connecting to the research areas sometime later. We'll be proposing that as a new areas in research chemistry. And also I encourage students to apply to IISERs and other institutes. Now he has already given the area topics where you can propose your summer research projects, because I see students always coming to me and asking, or coming to our faculty members, sir, what is the proposal? What should we write? They are struggling to write about 200 sentences, a research proposal. Now here, Dr. Musthafa has clearly said what you can write a proposal on. So, including the modification of electrolytes, what you can propose, even new ionic liquids are coming out as electrolytes. All these things, you can develop your idea. Only teachers and talks like this can only motivate students. This is very important, very significant, lot of funding in this area. So students, I am sure that many of you will take up this profession. So with these words, thank you, Dr. Musthafa, for your cooperation with us and associating with the Department of Chemistry, Devari College. We are looking forward to your support in all means. And also I thank all the participants for making use of this opportunity and coming to us, all the faculty members who are genuinely attending this course. We are very happy to have you here. Thank you, Dr. Musthafa, once again. Thank you very much.
Thank you, Dr. Manoj, Dr. Jamon, Dr. Tania, for inviting me for this wonderful event, and I have really enjoyed it. And I know that all your body language says that you are great teachers.
Truly grateful to you, Musthafa.
Okay, so I'm a regular visitor to Calicut, so I'll try to visit.
Definitely.
We hope to get you in person.
Oh, sure.
Okay.
Well, I have many friends, one Dr. Anish is in your department.
Yes,
Yes,
he's a
yes.
colleague.
Okay.
I
So
was
Yes.
there in NIT for a few years.
okay. So, my friend is there, Dr. Sujit.
Ah, yes,
Yes.
I know.
I
was
always
working
visiting.
with him also.
Okay, great. He's my close friend.
I was
So-
doing my first track project there.
So definitely,
Before joining Devagiri.
your next visit, by then we will not have corona issues, so we can have a luncheon meeting. We look
Oh, why
forward
not?
to that. We look forward. to
Sure.
that.
And a little bit of interaction with the students personally.
Definitely, for sure. Anyway,
Thank
thank
you
you very
so
much.
much, sir.
Yeah,
Thank you
thank
so
you very
much.
much, Tanya,
Thank
Jamon, and Manoj. Okay.
Okay,
Thank you very
thank
much.
you.
Yeah. Take care. Bye.
So we'll wind up the meeting, dear participants. Thank you all. Do visit us for the next talk also. From the next week, we'll inform you. So join us for the organic chemistry sessions. Thank you all.